Hello everyone, thank you for attending the workshop at the Reinforcement Learning Conference. So the study is about the weighted multi-step loss impact on the predictive error and the return in model-based reinforcement learning. Myself, Abdelhakim, Benechehab, a PhD student at Huawei Noazark Lab and Eurocom, along with my supervisors and collaborators Alberto, Giuseppe, Paolo, Maurizio, Filippone, and Balázs. So the problematic we want to tackle is in model-based reinforcement learning and is about compounded errors. So the setup is given a data set of real system trajectories. We want to learn a parametric model of the transition function of the environment. So that given a current state in action, we want to predict the next state of the environment. And the training set is a given number of trajectories sampled with some behavior policy from the real environment. And we want to train our parametric model by minimizing the mean square error or negative log likelihood for probabilistic models. So now, then at this time, when we look at the single step error of these models, it's pretty good, like something like 99% R squared. But when we look at this predictive error down the horizon, when we do long rollouts from the models, we have errors that are compounding and the predictive error gets very low. So the solution we propose is a weighted multi-step loss. So the elements of this loss are some horizon-dependent weights that sum to 1, some loss function, which could be a mean squared error, for instance. Starting from some initial state, we will roll out a trajectory of actions, and we have ground truth visited states from the transition function of the environment. Then, given all of these elements, we define the weighted multi-step loss up to some horizon h as the weighted sum of the loss or the error terms at every prediction horizon. So for the prediction horizon j, we will compose our model j times using ground truth actions and compute the error with respect to the state visited after j steps. All this adding these weights in order to stabilize the optimization. So this is a schematic representation. The error would grow with the horizon, and instead of taking only L1, which is the baseline that is done by default in model-based reinforcement learning, we suggest to have a weighted sum of all these error terms. And since they are in different scales, we need these weights in order to stabilize the optimization, as I said. So the results show that on offline datasets, when we have the setup of noisy observations, so additive Gaussian noise in the states, when we look at this aggregated R2 square at different prediction horizons, we see a huge improvement with respect to the baseline in a couple environments in datasets. Some of them are from the D4RL benchmark, for instance, and this improvement gets larger with the perturbation scale. Meanwhile, if we look at the offline model-based learning performance, so we take some agent like DINA style soft actor critic, very similar to model-based policy optimization, MBPO. Then in the noiseless case, we manage to improve a little bit over the baseline, but if we take large values of the loss horizon, like 10, this stops working because now the optimization is more challenging on the model side and we fail to get good policies using this. In the noisy case, it doesn't work in all cases because in this task, it's tricky to get it to work with even small-scale perturbation in these states. So the conclusion is that the weighted multi-step loss is useful to improve the predictive error down the horizon, but it is not necessarily a good metric for model selection in model-based reinforcement learning. Thank you, and don't hesitate to contact us if you have any questions.